Good afternoon, everybody. So my name is Maarten Breddels. I'm here together with Jovan Veljanovski, and I'm going to talk about modern data science with FACS, a new approach to data frames and pipelines. So let's introduce the team behind FACS.io. So I'm Maarten Breddels, former astrophysicist, freelancer consultant, working mainly on tooling on data science, Jupyter Core, Core Jupyter Widget developer. I work a lot with QuantStack. I am the founder of FACS.io and principal author of FACS, what I'm going to demonstrate today. And I'm here with Jovan Veljanovski, also former astrophysicist and senior data scientist. And together with Jonathan Alexander, they're responsible for steering the data science direction in FACS. And together with Mario, we work on front ends dashboards. So I'm going to say what FACS actually is, why does it exist, what makes it unique, and we're going to live dangerous and do a live demo. And if I have time, I'll show some extra features. So let me start with the PyVis landscape overview. Some people, so these are all Python visualization libraries, and some people say, well, oh, it's an unorganized mess, there's too much, needs to be convergence. I would say an optimistic view would be you can do anything in the Python ecosystem. We have so many to choose from. There's always a package that can solve your solution. And so what's the case with data frames? Do we have so many data frame libraries? Well, not yet. So the mother of all, Pandas, of course. And on top of that, we have Dask data frame. Let me start my timer. Yes, a few minutes late. And another, to scale up Pandas, and another version built on top of Ray and Pandas is Modin. S-Frame by Theory. Now, bought by Apple, not so well known at the moment. QDF by NVIDIA, has to run on a GPU, pretty fast. There's also Koalas that has a Pandas API, but it's using Spark. And today we're going to talk about FACS.io. And thanks to Mark Garcia, we're going to actually be in the same room at EuroSciPy, so we're going to see how we can work together. But what I think it's really important is the data format. And the Apache Arrow project is enabling us to basically talk the same data, at least in the future. It's still young, but I think that will happen. So what is FACS? It's a data frame library, like Pandas. It's actually the Python library FACS Core that is just the data frame library. And on top of that, there's support for HDF5, Arrow, visualization, a server for having remote data frames. And today we're going to talk a lot about FACS-ML for the machine learning integration and how you get automatic pipelines. Pip installable, Conda installable. You can be specific what package you want to have. So why does it exist? It's really memory efficient, so we'll show some of that today, due to the expression system it has. And with these expression systems, we'll show you, we'll have free pipelines. And we can also do just-in-time compilation to optimize our expressions using Numba, Python, and actually execute it on the GPU. And we're using HDF5 for storage. And together with the Arrow spec, we try to stay close to that, column-based storage and memory mapping. I'm going to demonstrate you can open a 1.2 terabyte file on this laptop in an instant and just work with it as if it was a normal data frame. Kind of the sales pitch of FACS is you probably don't need a cluster yet. It can handle over 1 billion rows on your laptop. String processing is really fast, and that just saves you time, money, and energy. I mean, if you don't need to spin up a cluster and keep it simple, that's only a win, I would say. And so let me say a bit what makes FACS unique. And why can it handle such large data sets? So let's represent a data frame by a dictionary, symbolically. And we have data, here an X column and a Y column. It's a bit small. And you have a state. And if I now say df2 is dfy smaller than 10, so I filter my data frame instead of making a copy. So imagine this was a 100 gigabyte data set, it would create maybe a 90 gigabyte copy, so that wouldn't work. So instead, what FACS does, it creates, it references the same data. The data is immutable, and it will keep in the state what this filter was. If you add a new column, x plus y times 10, in the state, it will add what we call a virtual column. So z is basically the expression, and if you want to do computations, it will do this computation on the fly and not take any memory. So this is true, but if we're going to do it, this is my lucky slide, and after this, all presentations, all demos work. So is this large enough? No? Is this better? Yeah. So we did some imports. Let's see. Is this still readable? No. So not on the back. So it's a bit garbled because it's so zoomed in. So we have a file 1.2 terabyte, Gaia. So I told you, 1.2 terabyte, you can open it. So maybe that went too fast. Shall I do it again? Basically what it does, it memory maps the data, so it doesn't have to do much. And if I print out the data frame, it will just read a few bytes for the first few rows and all the other columns. So maybe for fun, I should just do it again. Because I can. But we're going to work with this data set, 108 gigabytes, New York Taxi data set, 2009-2015. So several years of data. By the way, this was 1.7 billion rows. And this New York Taxi data set is 1.1 billion rows. So let's see what's in there. We have pickup daytime, trip distance, pickup longitudes and latitude, drop-off, etc. So we're going to split this into a train and test data set, because later on Jovan is going to do some machine learning. So we split it in just a small data frame, 150 million rows, and one of 1 billion. So we're going to first run Describe on it, just to get an idea of the what's in the data. But that takes a while to run. I mean, it's 100 gigabytes, still needs to read in that data, and I hear the fan spinning, so it's doing some work. But we're not going to wait, so let's do something in parallel. Why not open the data set again? Because it's memory mapped, it doesn't really matter if I open it once, twice, etc. It's all referring to the same memory. So I'm going to New York, and I want to know, like, what's a good tip amount? So let's take a look at what the average tip percentage is. So tip amount over total amount I'm going to execute. So tip amount. So we say 13%, 16%. So what this is not a series. This is an expression. So it's not taking any memory, and we want to do computations with it. So we're going to do tip per percentage. So we're going to add a virtual column. So now we added a new column to this data frame, tip percentage, and it's not taking up any memory. So let's do some computation with it. So what should I tip? So I should tip an infinite amount. Okay, that's not good. We had some divisions by 0, as you can see. So we're now going to filter the data frame, and this is 100 gigabytes of data that I'm going to filter and make a copy of. Well, Vex doesn't do this copy, so this actually runs in finite time, and you'll get an answer, 7%. Okay. So the fans are off, so probably ran Describe. So I'm now going to hand it over to Jovan.
Hi, everyone. So we were preparing the demo, and we really thought the best way to show Vex to you is to basically show you how it works in practice in a live session like this. So let's just jump into it. So as Martin introduced this taxi data set, I'm kind of worried that the data field will saturate, so I want to have a backup plan. So let's analyze this just in case something happens to the economy or something. So we have this data set. We're not very familiar, so let's do some EDA first. I start off by looking, for missing values. We want to get rid of that. That's never nice. So this NA, it's kind of like pandas. We'll see, okay, at the moment, everything is fine. Then we have these two columns, lots of missing values. We'll maybe see later what's going to happen. We have in the pickup latitude 1, and in the drop-off location, we have a bunch of them, and so on. some tags, people don't report it, not surprising, and so on. So I'm a taxi driver. I really care about a pickup location and drop-off location, so let's take care of that. Let's kind of zoom in. I'm just listing the columns that I want to drop. I will execute that. It runs super fast because nothing really happens. I'm just telling the Vex state, oh, when this eventually gets executed, I want these columns, the nonce in these columns to be dropped. Here, I want to explore the data frame more, and I see that the maximum number of passengers is over 200. That seems kind of weird, so I want to investigate it a little bit. And also the trip distance, I see the min max values. Well, one is negative, the mean value, and the maximum is very large, so I want to also take care of that. So let's do value counts. If you're a data scientist, value counts is probably your favorite pandas method. Here, because we have a billion size rows data set, we added a nice progress bar so you know how fast this goes. And you may think this is fast, but actually it needs to do some pre-computation because we added a filter, we had a train test set. So if we execute this again, actually it runs even more fast. Okay, so we see most of the taxi trips have a single passenger, then 2, 5, 3, and after around 7, we have some trips with 0 passengers. That's not good, and the rest is just basically noise and just spurious data. So I'm going to clean that to include only passengers between, well, with some passengers, but less than 7. Now let's look at the distance distribution. I'm going to plot a histogram. This is, again, billion points in real time, and here how it looks like. Big peak at 0. I'm not sure if it's really 0. I'm going to check. I want to ignore all these negative distances, and I want to, well, see what happens on this really positive tail. We really follow the Pandas API here, so checking if there are any 0 values is the same as if you do in Pandas, and we see that there are 7 million trips, taxi trips with distance 0, so that's not good. And just for fun, I want to see what's the absolute maximum distance that this data set have, and it's like ridiculous number. It's basically in miles, half the distance to Mars, and just 70 times to the Earth-Moon distance, so that's also not good. I want to get a better insight, so let's zoom in a little bit on this distribution, something that makes more sense between, let's say, 0 and 20 miles. We see that it kind of tails off after 10. I only care about the bulk of the taxi trips, so let's filter this between 0 and 10 miles. But so I looked into where this data set comes from, and this taxi company says, yeah, we serve the whole of New York. Is that really true? So I want to investigate this. With Vex, with the help of IPy widgets, you can interactively create maps like this with basically numbering billions of points. So this is basically New York, but there are some outliers that make this map well, unreadable. And I can zoom in a little bit, and this is a properly honest demo, so nothing is pre-computed. Every time I zoom in, the grid gets updated, the computations are done. If this wasn't so zoom in, you can see there is another progress bar here, so I can zoom in a bit more. And you see the computations, boom, you can pan. And I kind of see New York now. Let me zoom in a bit more. And there it is. So here I see that I don't really... So I can't really, well, I've not been to New York, but this is basically Manhattan and some airports, but you can decide of what you want to kind of select from here. So I've just decided on some ranges on the pickup and drop-off locations. Again, this is just a filter, nothing gets executed. I'm just updating the state. So it doesn't matter how many rows you have, it's just instant. Let's create some features. We want to explore, let's say, the mean trip speed. This is just trip speed divided by time, by duration. Let's also introduce duration and some other metric that may be interesting to us. So, okay, let's investigate the distribution of mean trips. So now this is actually a virtual column, like Martin described. So when this cell executes, what it does, it actually in real time executes, well, this expression and bins it. So for 1 billion rows, this takes, well, 11 seconds, so that's not bad. We can do this kind of in real time. Again, we see there is some negative durations, and then there is a big positive tail, not really reasonable. Let's zoom in a little bit more. Yeah, let's do another histogram of 1 billion points in real time. And so I don't know if anybody is from New York here. I don't know how long people spend in a taxi, but this is up to 1,000 minutes, so that doesn't seem reasonable to me. Well, let's make a cut between, well, 0 minutes, just a little bit more than 0 minutes, and 2 hours if somebody really spends that much in taxi. So with cleaning the data set a little bit, little by little. Now let's look a little at a few daytime features. Just like in Pandas, we can extract from the pickup daytime, hour, day of week, month. We can add other features that designate whether something is, a trip has occurred in a weekend or not. Next, this is just internal for Vex. It really speeds things up. Basically, I'm ordering the pickup hour and day of week, and it allows me to do plots like this. I really want to see the number of pickup of pickups per given day and given time of day. So this is an honest demo. It really runs everything on this laptop in real time. It sometimes may take a few seconds. And this is what the data frame the result looks like. We can see this here is when we have the most pickups. Kind of makes sense. And during the working days, in the evening, we have more pickups. Here is the absolute peak. Friday night, Saturday night. This Sunday spot here is really Saturday night, just after midnight. And of course, in the morning, we don't have that many trips. Next, if I want to be a part-time taxi driver, I want to see, okay, which parts of the day are more profitable for me. And I'm also kind of young, and I want to drive fast, so I want to know when I can drive the fastest. So here I can do group by. The API is exactly the same with Pandas. However, it's done fully in parallel. And out of course, you can use as big of data set as you can fit in your hard drive. So this is how the resulting data frame looks like, and then you can plot it with your favorite tools. I'm using Matplotlib and Seaborn, and you can check that this makes sense. People tip the most in the morning, 8 and 9, probably they're happy that they made it to work on time, and in the evening, after their happy socializing time. In terms of speed, you can drive fastest early hours in the morning, probably not much traffic, so here is the traffic jams, considerably slower. I'm going to skip this, nothing failed, really good. So now my CEO taxi boss, I can investigate the data frame again, and here you can see all the extra columns I've added, the time of day, the weekend, so on, without cost of any memory whatsoever. So now I want to do a little machine learning project. I want to predict the typical duration of a taxi trip. So I'm going to import VexML, which hosts a bunch of modules for typical pre-processing, but this time they run fully out of core. We're kind of following the scikit-learn convention here. Here, I want to show you something else that we think it's cool. I'm going to add another feature, this arc distance. So this is as the crow flies between the pickup and the drop-off locations. And just to make sense, I'm calculating it here. But this is a very complicated expression. It has a lot of trigonometry, algebra, and so on. So if I add it as a virtual column, and let's say I want to do some computations with it, let's say a sum, even though Vex is really, really fast and parallelized and optimized and all that, it does take some, maybe 20 seconds or so. And this is kind of fast already, but if you happen to have a GPU on your machine, you can use, as Martin said, CUDA to optimize your code. So I can do just that and calculate this expression once again. And now it really, you get around 4 times speed up compared to the CPU. I can choose which virtual expression I want to use. And let's say you don't have a GPU, like I have a Mac, so I can do this. Let's do another complex expression, but here you can use just-in-time compilation with Numba or Pytran to, again, optimize your expression. And the cool thing about this is now when you have this computational graph and you execute it, you can use both your GPU and the CPU at the same time, so you're really pushing your machine to the limit. And now I can, again, view my data frame with all these extra expressions that I added at no extra memory cost. All right, so now I want to do a PCA, for example. I want to pre-process this data set, so I'm just running PCA on the pickup and drop-off locations. The reason behind this, I want to show off the fast PCA, but also this is a big tabular data set, and we kind of know as data scientists that tree models or gradient boosted models work really well with tabular data sets. And the idea behind it is that in the US, most cities, including New York, their streets are kind of on a grid, so New York is kind of like this. You will see now, once the plot gets executed, if you use PCA, so you get these principal components, and your streets get aligned like this, you can use less features, and your splitting of the trees will be more effective. So we can use it as a trick, as a nice pre-processing technique to get a little bit more optimized models. And this is basically what I mean by this. So the streets are more aligned to the coordinates. All right, then I have this payment type. I can see all the individual options that people the taxi drivers used to record how people paid. And I'm also using string preprocessing function, and I do this in real time for 1 billion points. And this is all the options that the taxi drivers used. From the documentation, I know there is only a finite amount of things that they should have done, so I can just simply encode this using map. Just like in Pandas, I can make a dictionary and map it out. And even though this is 1 billion points, we're using optimizations in the background, hash functions, parallelization, so this takes only a fraction, only a few seconds, 10 seconds. Now I can again see the data frame, and I can see all the extra columns I've added, the PCA, the payment type. This is just a preview. Now I'm kind of happy with my feature engineering. I want to model this. I'm going to select, oops, I'm running this again, doesn't matter. I'm choosing which columns I want. This is my target column. I'm going to import a LightGBM wrapper. You can use it the same way as you're using scikit-learn. And I'm going to train it, but I'm training it on a small subset of the data because scikit-learn is not, LightGBM is not really out of core. Here, now once it's trained, I can use to predict. Typical predict method gives you an in-memory array of the prediction. However, if you use transform method on your model, you can add your prediction as a virtual column in your main data frame. And this is quite powerful, actually, because now it gives you a really easy way of doing ensembling. Oh, you can check your performance, but this is meaningless. I didn't do validation. So let's add a second estimator, because maybe Martin thinks, oh, linear models are also great. You shouldn't ignore it. But linear models require better handling of categorical features. So now I'm going to one-hot encode all these categorical values that I had. And again, I'm doing this for the full 1 billion rows in real time. After this is done, it's going to take around 10 seconds or so, 20 maybe, because it's a live demo. I want to standard scale these numerical features that I added, so the arc distance, direction angle, and trip distance. And here, because this laptop happens to have a GPU, I'm using the GPU and the CPU at the same time while this standard scaling is going on. So this is just subtracting the mean and dividing by the standard deviation. Once this is done, okay, you can see that this took only 23 seconds. This is going to take more or less the same. I can just import the scikit-learn wrapper. We're compatible with all scikit-learn models. You can just use them out of the box. Choose the features that I want to use. Train, again, transform. And once this is done, you can view the data frame. And now you see all the, let's say, the one-hot encoding columns we made. There are many of them. The scaled features and the linear prediction. And one advantage here, because we're using everything so consistently, you get to keep the column name, so you always know which column came from which transformer, from which process. We can do now easy assembling. You can just simply average your two predictions, or maybe add weights if you want. And again, this is propagated throughout. Oops. Fully throughout the pipeline. So actually, now comes my favorite method. The power of this, adding stuff as a virtual column, is now, let's say I'm happy with this. Imagine that I've done proper cross-validation and I want to try it on the test set. Oh, but I didn't build a pipeline, so I have to go back and redo all this. Actually, we have been doing a pipeline all along automatically in the background, because every operation we did just updated the state. So all we need to do is to propagate this state to a new data set, is just to save it. We can save it to disk in a JSON. And now I'm going to open up another notebook, fully different kernel. I'm going to load up Vex, the same data frame. I'm going to redefine the test set. We didn't touch this. We can investigate it, just a bunch of columns, the ones that are on disk. I'm just going to load the state that I just saved into memory. And now once we view this test set, we see all the columns we defined automatically for you done the PCA, the LightGBM, all the one-hot encoding, and all the way to the predictions at no memory cost whatsoever. Well, you can check the performance, a bit meaningless. And now including all the memory, all the columns that we added, we see we have 88 for 100 million rows in the test set, on a simple laptop without any problems. So that was the live demo. Martin will wrap this up, and thanks.
think I have a few more minutes. Just want to mention, like, we're using this. There's a project that I'm doing with the Space Telescope Science Institute, where we deploy VEX on the server, and so you boot up a AWS machine, and then you need to wait until you copy the 1.2 terabyte file, and that's really annoying. So what we did is have streaming S3 support, so you can rev it S3 file, and even if I didn't have an internet connection, this is already, some of it is cached on my disk, so you basically can work with like data frames from S3, put this notebook anywhere and don't have to change the path. For instance, I executed this before, so this is already cached on my disk. And something really interesting is that because we make this distinction between data and state, actually for many cases we don't need the data, we just care about the state. And the state only changes at the client. So in my notebook, if I add a virtual column, the state gets updated, and I can send this to a server where the data is, and that can actually do the execution. So let's see if we have an internet connection. Yeah. So I can ask like remotely to give me this plot. So this is a Gaia data set. So we come from astronomy. What you're seeing here is actually 1 billion stars from the Milky Way. Maybe interesting to know. And you can actually do computations on remotely on these expressions. So I think that's quite an interesting side effect of this. So I think we did well. Lucky slide. Let me conclude. So I hope or we have convinced you that VEX is a quite fast and memory efficient data frame library. And actually we forgot to show you how much memory Jovan was using. So this is his notebook. So he was using at maximum 3.7 gigabytes of memory. I think that's pretty decent for a 100 gigabyte file. Oops. So just to give you an order of magnitude, like what you can expect. So on this laptop, 1 billion rows, 1 terabyte of data. That's kind of the sweet spot for VEX. We've shown you this concept of using like immutable data and state, where the virtual column lives, and the filters giving you the option to do this on this laptop, but also to allow you to do to optimize your expression using Numba, Python, CUDA, and you can even do like things like derivatives. And I think what's really convincing is that this state remembers your pipeline. And it's actually an artifact. So if you have something and you're happy with, you're done. You don't have to like redo a pipeline. And that makes it really easy to for deployment. And I also showed you some S3 support and the option of having remote data frames. So if you can read it, and you cannot, I guess, some of the resources here. The talks are also online, and we're probably gonna publish some new articles the coming half a year. So if you follow us on Twitter, Maarten Breddels or VEX.io, you'll stay up to date. And now we have some time for questions. Thank you.
Okay, cool. Do you want to pick who you want to take the questions from?
Yeah, thanks for the amazing talk. Just one quick question. Is there any significant part of pandas that you couldn't replicate yet? Is like any part of pandas that is not yet implemented? Any significant part, I assume?
So I think there are some things like that are in pandas that just don't translate to this, like the option to transpose a data frame. Like if you would have a billion columns, that wouldn't make sense. So that definitely, well, I keep saying like, no, it cannot be done, and then like a week later I do it. But so like a half a year ago, I thought that group by wasn't possible, and it is. So yeah, do you know is there something crucial missing? Probably there is. I mean. Can you do multi-index? So one thing that that we don't have is an index. And yeah, and it's also like I don't fully agree with the idea of having a single index. So I think it mixes the concept of having like a primary key and an index. So I'm still thinking how to like implement this by having like multiple indices and, yeah, still thinking about it.
Hey guys, it's awesome talk. I would like ask different question. What are the limitations in terms of your like laziness and memory map files, for example? Is a join supported, or is it impossible for Wix in general to do merge like pandas do? So what are the limitations of the framework and the mindset behind the framework? And another one, did you consider to contribute some of those features to like pandas or to other ones rather than create a new one, yet another one?
Yeah, good questions. So what was the about join? So there is a join because we had to do in astronomy. We had to basically join a 1 billion row table to another 1 billion row table, and I just created like a really simple Python implementation, and that took, I don't know, 10 hours or something. So I just ran it, and the next day it finished, and we wrote it in the same order as like in the join order, so we can also memory map that and do basically after that I do an instant join. There's now a PR open by me that does the join using like C++ with the fast hash mapping, but we don't use it a lot actually. But yeah, that will probably happen within half a year. And contributing back, yeah, that's a difficult issue that has to do with like funding, who's doing the funding, how much free time you have. I would love to collaborate, and we're gonna talk at Euro SciPy to the other data frame developers, like what we can do. So I would love to, but yeah, if you have funding, then let me know.
Hey, thank you very much for a very good talk. I have a question. Do you support sparse data? Like, can I have columns which have very few non-zero entries, like million of them? Shall I rephrase?
Yes, please.
So, do you support like sparse data? So, can I have like a Versmoy file which contains like million columns and like million rows, but with very few entries? Will your machinery support that? Yes.
I did it a while ago, like support, just to see how it would go for sparse, but a particular format. Like it's like you only have a few rows that are available, and but not so many columns. But again, like most of the features that we put in are like basically on request. So we work with the client; they need this. So we haven't encountered much of this. But yeah, that I think. Actually, a better way to answer that is to wait for PyArrow to solve this. I think they're now working on sparse, and a lot of these questions are actually like, yeah, maybe we should wait for PyArrow to like solidify this so we can build on top of that.
Another question, actually very related. So you mentioned Apache Arrow support. Is that zero cost conversion, or do you need to actually go through all the data and make it compatible with the format?
So if like all numerical types are supported and strings are supported, booleans, but not yet the more complex types, not yet. So, but from my side, they're zero copy. I don't know what Arrow does internally. I've done so there are like lots of methods in Vex to go from pandas data frame to Vex data frame or back, or to an Arrow table and back. And some of them take some memory, but I didn't look into that. But it doesn't like copy like like for this data set, it wouldn't use like 100 gigabytes. It would do a shallow copy. Yeah.
Excuse me, do you mind passing this down?
Hi, so this looks like a ridiculously good tool for analysis. I was wondering how it performs in a more sort of ETL style framework. So if you actually had to write out all of them extra columns that you added, what's the sort of performance there?
Can you repeat, please, what you mean by...
Yeah, so when you added all the columns as virtual columns and then you saved it as like a JSON blob that you could use elsewhere, what if I wanted to rewrite the original data frame, like the entire terabyte, but with extra columns that I've computed?
He wants to write it out, I guess. So you want to like materialize this on disk?
Yes.
Yes. df.export.
Is it performant?
What was the question?
Is it performant? How long would it take to write? Because one of the advantages of, say, Spark is that it can write in parallel across many.
I would say it's disk speed limited. I think I don't do it a lot, but I've done it like for the Gaia dataset, like a lot, like making subsets and exporting them such that you don't have to pre-compute.
So actually, if you want, I don't know if this benchmark would apply for this data set that we used, because it came in CSV format and we joined them and we exported as 107 gigabytes. On my laptop, which is a bit older than this, took maybe 30 minutes, around 30 minutes, not more than 30 minutes.
Yeah, cool, thanks.
So very nice tool. Just a question. Does it make sense for VEX to be used on small? I get that it's very nice for big data set and terabytes data frames. Does it make sense? Does it have any advantage on smaller data frames with thousands and hundreds of thousands of rows? What is, if there is an advantage, what is the advantage or disadvantage with pandas? Do you think it still makes sense to adopt VEX for smaller data sets?
So I don't know about all the methods, but apart from apply that we also have in VEX, which is not parallel, we have everything else parallelized, so it uses all the cores all the time. If you want to do some interface with our pre-processing tools, because everything gets memorized into the same data frame, you never lose track of, you get the column names labeled. For example, if you do one hot or frequency encoding or PCA, everything gets smartly labeled. So this is something that I like, because when I pass through things through, let's say scikit-learn, I get a NumPy array and I kind of lose the label, so I have to be, it's nice, but I have to be more careful of what's what. So that's one advantage. However, maybe we didn't mention this, so we're fully, I don't know what's the right word, we're fully compatible with pandas in the sense you can import and export a data frame to pandas without a memory copy, as long as you can fit it in memory without problems. So if there is something that you prefer in one library over the other, you're not locked into one system.
Yeah, and especially if like if everybody starts using Apache Arrow, then you can like change libraries quite easily. But I would say like if you have an up to like 10 million, maybe 100 million, Pandas performs great, and why would you change? Maybe because you want to do the automatic pipelines, that would be useful. But I would say like above like 100 million, it makes sense to start taking a look at VEX. Yeah.
Well, also, if you want to do string transformations, because we use C++ code in the background, those are significantly faster, regardless of size.
Okay, and just a curiosity, if I may, how long did it take the implementation of the library of VEX? When did the project started?
Yeah, so also an answer to like contributing is like it started 5 years ago, I would say, but it wasn't a data frame library, but more on like visualization for this Gaia data set. And slowly, like it evolved towards being a data frame library. So we kind of like used it internally, and we, especially Jovan was using Pandas. So it kind of grew to that API, because then I didn't have to explain what to use, and it's just easier for people to switch. And it's an API that everybody knows. So it slowly went this direction. I think starting from 2 years ago, it started becoming like a real data frame library.
Yeah. Hello, do you have any native support for the Apache Parquet format? Or should we use PyArrow as a bridge?
Yeah, so we get that for free from PyArrow.
Okay.
Yeah. Yeah.
What does the word VEX actually mean?
Visualization and exploration, it used to be. Yeah, but yeah, it's now just a name. Yeah. So I'm not allowed to change it by the people around me. They love it. So. No.
Any more questions? Sorry, do you mind passing it down?
Apologies for an awkward, non-technical question, but it's about the open source model. Because you do consulting and you also have an open source project. How do you solve this conflict of interests for a feature? Should it go into a proprietary client code or should it go to the open source version?
No, so all of it is open source. So there's no proprietary code in the whole project.
But you mentioned before that a feature depends on funding. Like if there's a client who needs a feature, then it will eventually go into the library at some later point.
Yeah, so if we, I mean, we're developing it together, and by together, I mean he does 90% of the work and I complain. But if it's some feature that we need, that we think the entire community or the majority of the community will benefit, we'll do it. If you come from a niche field or your application is really only applicable to you or your field, then to get priority, because we're just 2 people or 3 people, that's where the funding comes in.
But let me say that I wouldn't be interested in doing work that for closed source. I basically wouldn't take that work. That's not interesting, and I think not smart also for the companies, because who would maintain it? They would have to pay me again. So that wouldn't be smart. Nobody's listening, right? No.
Okay, unfortunately, that's all the time we have for questions, so let's give them all a round of applause, please.